All right, so we start the year off, chapter 1. We're going to get into a few things that I'm sure you've already heard about, you've talked about in your previous math classes, but we're going to go into a little bit more depth with you here. Some of the basics of geometry. So the first two sections here, we're going to identify points, lines, and planes, talk about segments, their length, and what it means to be congruent. And so for, again, this first day, the objective behind this, by the time you're finished here, you should be able to remember some of the basic concepts of geometry that you studied before, and now be able to name and sketch some figures. And again, after we learned about points, lines, and planes, we'll talk about segment postulates and identify congruent segments. Okay. Here are the standards we're going to hit. You're free to look at those at your leisure. Okay, so as we start to develop geometry, and as we start to develop the new language, the new concepts, the new everything there is for geometry, you always start with some undefined terms. These are things that we know exist, we know we're going to use, but and we can describe them, but to define them is a little bit differently. Is a little bit different. Those undefined terms are point, line, and plane. We'll start with the point. The point is the basic unit of geometry. Everything is made up from points. It has no size, is infinitely small, and we use points to show location. So in other words, there's no dimension to a point. Okay? It looks something like this, where we'd have a point, and then we'd have some capital letter, block letter next to it. As a matter of fact, that's exactly how we would name it. We would name this guy point A. That's it. Just write down A. Okay? Like I said, we use it to show location. A line, now if you start putting points next to each other and side by side, then they start to create another figure. And that figure is a line. So it's a line is a straight arrangement of points. There are infinitely many points on a line. A line has infinite length but no thickness and extends forever in two directions. And so it would look something like this. Now we can't draw to infinity. So what we do is we put arrows on the end of the lines to show that it goes in two directions forever. Extends forever in two directions. And there are an infinite number of points, but very often we will at least show 2 points on that line, because that's how you name it. You use any 2 points on that line. You could call this line AB, or line BC, line BA, but we have to use the line symbol above. The line symbol is just an arrow, just a symbol that looks like a line, so that we know that we're talking about a line. Okay, make this A little bit better. There's going to be a reason why, but the symbols that we use for these names are very, very, very important. It helps us differentiate between lines and segments and rays and things like that, so we have to have the right symbol. Okay? Now, sometimes we may not want to show the points on the line. I mean, there are points on the line, but sometimes we don't want to show them. So instead, what we'll use to name the line is a lowercase script letter, like L. So we can also name this line, line L. Okay? And that's it. We just use the L for lines. You can certainly use other letters besides L, but that seems to be the most common one. Okay? Now planes. A plane has length and width, but no thickness. So I didn't mention this, but lines are in one dimension, so points are no dimension. Lines are one dimension. A plane offers up a second dimension, so this is going to be 2 dimensions. Okay? It has a length and a width, but it doesn't have a thickness. Now, it extends forever in those two directions, the length and the width. So while it has a length and a width, we don't actually measure it because it goes forever. Okay? When we draw a plane, we typically draw like a slanted rectangle or a slanted box like that. And we need at least 3 points in this plane. And we'll talk about collinear in a minute. But the 3 points need to be non-collinear. It takes 2 points to create and name a line. It takes 3 non-collinear to create and name a plane. Okay, so if we have point A, B, and C in there, then we call this guy plane, and we use the word plane, A, B, C. Now, we could also, again, if we don't want to show the points, we could also use, instead of a lowercase script letter, an uppercase script letter. So something like P. And so now we could call this guy, well, I can't really see that, but uppercase script P for plain P. Okay? Use either one. Either 3 points with the word plane in front or capital cursive letter. Okay? Now, before we get to it's important to have you at least think about this, but geometry becomes useful only if we can find a way to model the world around us using these different geometric figures, points, lines, planes, or whatever else. So I would encourage you to stop the video now, look around the room that you're in, and see if you can't figure out what you would let a point represent, what you would let a line represent, or what you would let a plane represent, to try to figure out a way to model using geometry. Okay? You can stop that now and start the video back up when you're ready. Okay? All right, so we're going to move on. We've got some more definitions here for you. Definitions, vocabulary is a big deal. Got all kinds of vocabulary on our tests. But now collinear. If we want to talk about collinear, co meaning the same, and linear has the word line in it. Collinear means that things are on the same line. And we very often talk about collinear with points. And in order to talk about collinear points, you have to have at least 3. If you think back to Algebra 1, when you were graphing lines, generally speaking, you needed 2 points to make that line. Any 2 points will create a line. So it takes a third one to decide collinear or non-collinear. And so here, collinear means on the same line. And so in this first picture here, those 3 points are obviously collinear. Now, if that point in the middle there slides off the line even a little bit, then that becomes non-collinear. Okay? All right. Coplanar. Co meaning same. The word plane being in planar means that things are on or in the same plane. Now, it takes 2 points to make a line. It takes 3 points to determine a plane. So we would need a 4th point. So any 3 points will create a plane. So any 3 points will always be coplanar. We need that 4th point to determine coplanar or non-coplanar. So if these 4 points were sitting on a table, then they'd be coplanar. But if one of them slips through the table and falls down to the ground, then those guys would be non-coplanar. They're not in the same plane anymore. Okay? All right. So let's try here. We want to find, from this picture over to the right here, 2 other names for line PQ and 2 other names for plane R. And then try to find 3 points that are collinear and 4 points that are coplanar. Okay, stop the video, give it a shot, start it back up, and see what you come up with. All right, for line PQ, 2 other names for line PQ. We can actually just turn the points around and call this line QP. Or, if you look, there's a lowercase script n here, so we could also call it line N. for the plane. Plane R is that pink plane there. It takes 3 points to name a plane, so we could call this guy plane, what, VSP if you want, or plane VST, and there are other options. Plane VPT, plane VTS, plane PVT. I mean, there's a never ending, right? Just use any 3 points that are in that plane, and you would be fine. Okay? 3 non-collinear points in that plane, and you'd be okay. Okay? Now, 3 points that are collinear. And believe it or not, in this picture, there's only 3. Those 3 points are S, P, T. 4 points that are coplanar. Believe it or not, there are only 4 in this picture as well, and it's V, S, P, T. Okay? So hopefully you're able to get to that. All right, definitions again. Segment, line segment, ray and opposite rays. So once we've got these undefined terms, we can start building definable terms from these 3 undefined terms. So first is a line segment or a segment. A line segment is if we take a line and instead of letting it extend forever, we chop off both ends so that it stops. And so a line segment, by definition, consists of 2 points called endpoints and all the points between them. So something like, if we start with a line and then we chop the arrows off, chop the ends off, because it may be necessary to focus in on just a piece of the line, especially if we want to start talking about length, being able to measure stuff and all that. Then we chop off those arrows. Now it has an ending. Now we can measure. And so we have line segment AB. How do we name it? Well, in a line, you can name it, now I'm not sure I mentioned this, but you can name it using any 2 points on that line. It doesn't matter. But for a segment, you have to use the endpoints, because the endpoints tell you where it starts and stops. It tells you where to begin and finish measuring. So if I put a point in here, point C, I would not be able to use C in the name of segment AB, because segment AC is very different and much shorter than segment AB. Now, when we name it, we use the endpoints A and B. Our symbol, we have to put a symbol above so that we can differentiate between things that we're naming, but that symbol is not going to be like the line symbol. It'll be just like a segment here, where you chop off the arrows and just have a stick above AB. Okay? A ray consists of an endpoint. It starts at an endpoint, which is kind of weird, but it starts at an endpoint and then goes in a direction, extends forever in a particular direction. So there's a directional point. And so a ray starts at an endpoint, and here we want to call it A in the definition there. And then we have to have a point that gives the ray a direction. I could draw a ray this way, or I could draw it this way, or I could draw it this way, or I could draw it this way. And so I have to have a directional point. And so if we draw it this way, then B must sit here. Right? And so basically it looks like a line where we've only chopped off one end. Now you can't really measure a ray because it extends forever in one direction. Okay? But we use rays to construct other things. Okay? Now to name this, we name it from the endpoint first. We start with an endpoint, and then we use the directional point to give it its name. So we would call this ray A, B. Okay? Oh, by the way, if we back up to the line segment, we could call this guy segment BA. It's the same thing. Okay? We would not be able to call this ray BA for the ray because it does not start at B. That ray would be different. It would start at B and go through A forever. So this would be wrong. So would this, even though technically speaking the symbol makes sense, but we write left to right, we read left to right, so we don't want to do this either. We want our symbols to go left to right as well. Okay, so we want to stick with AB. Now, if you're looking for another way to name a ray, if we stuck another point here, C, we would be able to use the C here and call this ray AC. Because again, all we need is an endpoint, which is our starting point, which is weird, and we need a directional point, and point C can be that directional point. Okay? Now that we have rays, we can talk about opposite rays. Opposite rays are rays that share the same endpoint and go in opposite directions along the same line. Now think about that. If two rays are going to share the same endpoint and then go in exact opposite directions, what's that going to look like? Right? And I'll put it above here of that advertisement. So there's a ray, ray A, call it AB. And then if I want an opposite ray, it would look something like this, which, if you look at that, kind of looks like a line. Kind of looks like a line, right? Opposite rays make lines. If I were to name it, I would need to talk about ray AB and ray AC as opposite rays. And you have to name them that way. Start with the endpoint and then give the directional point, and that's the way the symbol's going to go, with the arrow above the directional point. Okay? But those guys are opposite rays. They make a line. All right. Let's try to come up with another name for segment GH, and then name all the rays with endpoint J, and then which of those rays are opposite rays. Give that a shot. Stop the video, give it a shot, see what you come up with. You can start it back up and check your answer. Okay, so we're going to give another name for segment GH. The only way we can do this is to turn this around and make this HG. Okay, there's no other way to name a segment. Not like a line where there's an infinite number of ways to name it, and even a ray has more than a couple. Now, name all rays with endpoint J. That means that every one of your names should have J in the beginning. So we can go JG, JH, we can go JE, we can go JF. And if you're looking, these guys and these guys are your opposite rays. They're the ones making the straight lines. Okay? Hopefully you were able to get that. All right, sketching. Got to be good about drawing. Sometimes this is just using some tips and tricks to make the picture look the way you want it to. So if we want to sketch a plane in a line that is in the plane, we need our plane, which is just going to be a box. And then make sure that when you draw the line, make sure the line stays completely in the plane. Okay? Don't let the line go outside the box. Okay? Now, obviously, if you want to sketch a line that's not in the plane, then you want to sketch that line to where it's not even touching, not anywhere inside or touching the box, the plane. Okay? That's going to be a pretty good indicator that the line is either in the plane or it's not. Now, the last one here says sketch a plane in a line that intersects the plane at one point. So we can draw our plane. Now, I want the line to intersect the plane at one point. That means that part of the line needs to be inside the plane and part of the line needs to be outside the plane when I draw it. I like to do this. So I'm coming out here. We have to make this a three-dimensional picture. The plane is in 2 dimensions. I need the line to come out of that plane, so it's going to introduce a third dimension. So we have to be good about creating 3-dimensional pictures here. And the way we do that is anything that you are not going to be able to see, you use dashed lines to show that. So maybe the line would come right here and then come out of the plane. Okay? And so now we have a line where part of it's drawn inside, part of it's drawn outside, and the part that you would not be able to see in a three-dimensional picture is dashed. Okay, so that would work well enough there. The harder one to draw are two planes that intersect in a line. Let me see if I can't help you do that. First, you're going to need to draw a plane on your piece of paper. Now, we have to come up with a plane that's going to go the other direction. So this is going left to right. I need a plane that's going up and down. And the way I do that, again, there are going to be parts of this plane that I'm not going to be able to see. I'm going to draw my second plane first, and then I'll worry about parts that I'm not going to be able to see. Okay? Now, I would not be able to see right here. I would not be able to see right there. I would not be able to see there. And that's probably it. Now I'm going to draw the line through here. I think that's pretty good there. It's a pretty terrible drawing, but there you go. Okay? And just do the best you can. Just try to show the places that you're not going to be able to see. Okay? All right. Now, segments and congruence. Segments, like I said before, we're going to create a line segment so that we can measure it. And when we name a line segment, we use the two endpoints and then the segment symbol above. When we measure it, we have a numerical measure. There's a difference between talking about the segment itself with the name versus the numerical measure of that segment. Which might, and then when we talk about the numerical measurement, then we want to write it as this. We can put a script M in front of the name segment AB, which means the measure of segment AB. Or we can just drop all the symbols all together and just use AB, which means the length or the distance from A to B. Okay? And so we'll use those. You'll see me use this, the no symbols at all, more than you will the M in front of the name. Okay? But they both mean the same thing. Now, postulates. You're going to get introduced to your first postulate. And a postulate is a rule that is accepted without proof. These are things, when we go through the postulates, when we talk about them, they're going to seem incredibly obvious, and you're going to wonder why we're even talking about them. But that's why we don't have to worry about proving them, because we know they're going to be true already. And the reason why we talk about them, we bring them up, is so that they become part of what you try to use in your geometry. Okay? And so the first postulate here is the segment addition postulate. The segment addition postulate says that if you have a segment and then a point somewhere between your endpoints, it doesn't have to be in the middle, it could be anywhere, it doesn't matter, then we know that if we measure the length and find the length of AB, add that to the length of BC, then that's going to have to add up to the length of the whole thing, AC. Okay? That makes sense. I think that makes sense. Okay? Since AB and BC are on the same line and they share an endpoint, you should be able to add them together and get the bigger segment they create, AC. Now, on the other end, on the other side, if we know that AB plus BC equals AC, then B is between A and C. So it kind of works the other way around, too. We can use the postulate to prove if points are on the same line or if one point's between two other points. Okay? All right. The next postulate we're talking about is the ruler postulate. The ruler postulate helps us measure the length of a segment, okay? Yes, we would use a ruler to measure the length of a segment. But more importantly, what happens if you don't start at 0, right? When you use a ruler, you don't have to start at 0. The ruler postulate says that you can put the endpoints on any two measuring ticks of a ruler that you want. So S lines up with 2 centimeters here, and T lines up with 5.4 centimeters here. If you do that, then to find the length of ST, then you would simply take 5.4 minus 2. Make sure that you're taking the absolute value, only because when we subtract, sometimes we can get a negative number, and we want all of our lengths to be positive, so it's the absolute value. So anyway, we're going to subtract those two coordinates. We're going to subtract those two numbers that the endpoints line up with to find the true length of ST, which is 3.4 centimeters. Okay? I don't for a second pretend to believe that you guys didn't know that already, but again, it's worthwhile just mentioning so that when we start using our geometric tools, we'll be able to use them correctly. Okay? All right. Now, more appropriate use, or the use of the segment addition postulate. So, the cities shown on the map lie approximately in a straight line. Use the given distances to find the distance from Lubbock to St. Louis. So, Lubbock, Tulsa, and St. Louis are all on the map here. From this map, hopefully we can see that the distance from Lubbock to St. Louis is simply going to be equal to the distance from Lubbock to Tulsa plus the distance from Tulsa to St. Louis. That's your segment addition postulate. And I think it's very helpful when you know you're going to use the segment addition postulate, or when you're looking at a segment with a point between the endpoints, to go ahead and write the segment addition postulate out with the segments, with the segment names, like I did here. LS is equal to LT plus TS. Because now you can just plug in numbers and figure out from there what kind of arithmetic you need to do to find what you need. This is going to be easy enough. LS we don't know the length of. LT is 380 miles. TS is 360 miles, and so that means we just add those together to get 740 miles. And that's the distance from Lubbock to St. Louis. Okay? Now, that seems pretty obvious, and so maybe you don't need the segment addition postulate for that. But there are times where you're not going to necessarily just add two numbers together. Here we've got segment FH with G in between F and H. And we want to find the length of GH. Well, if we use the segment addition postulate here, and we want to, we look and we see that FH, the whole thing, is going to be equal to FG plus GH. Do we know the length of FH? From the picture, we do. The length is 36. Do we know the length of FG? And from the picture, we do. It's 21. So how do we find GH? Well, this equation suggests that we subtract 21 from both sides, and we find that GH is actually just going to be 15, which again is an oversimplified version of how we're going to use the segment addition postulate. But just so you're not always adding numbers together, you need to set up the postulate, plug in numbers, and then do whatever arithmetic is dictated there. Okay? All right. Now that we can measure segments, that allows us to talk about congruence. Okay? Congruent is the geometric fancy word for equal or the same. So two segments are congruent if they have the same length. Okay? There is a difference between talking about the lengths of two segments being the same and talking about the segments themselves being the same. The difference is, in one instance, we're talking about the actual numbers, the numerical numbers that are equal. The other one is talking about two figures that are the same. So if the lengths are equal, then we can say that those, they're numbers. AB and CD are lengths, they're numbers. We can say the numbers are equal to. So AB is equal to CD. If we're talking about the segments themselves, AB and CD, then we can talk about segment AB being congruent to segment CD. And there's a difference in the symbols as well. If it's equals, it's just equals. If it's congruent, we use the equal sign with the tilde above it, a squiggly line above it, and that means congruent. This guy right here is your congruent sign. Okay? All right. Let's use this. Plot. Let me back up for a second. I wanted to show you this. If two segments are going to be congruent, then we will use these tick marks to show that. If two segments, in a diagram, you're going to know that two segments are congruent if they have the same number of tick marks. Now, the number of tick marks do not matter as long as they have the same. You could do 1, you could do 2, you could do 3, you could do 4. And sometimes it is necessary to add tick marks so that we can differentiate between sets of congruent segments. Okay? All right. And now back to this. We have 4 points here that have coordinates. And now we want to get into the coordinate plane. And in geometry, again, it's all about modeling. Sometimes it's helpful if we can take a geometric figure and put it in the coordinate plane to help us give numbers to points, give coordinates to points. And so these 4 points have these coordinates. And if you plotted those out, these segments would look like this. You would have segment JK and segment LM, and that's where they would sit. Now the ruler postulate helps out a lot here. Where since in a horizontal line, the y coordinates are going to be the same, the ruler postulate helps us in that all we need to do is take the x coordinates and subtract them. Okay? Or if you want, an easier way to look at it is just count. How far from J to K? And this only works for horizontal and vertical lines. So the length of JK, if you were to count from J to K, you'd go 1, 2, 3, 4, 5. From L to M, we would go 1, 2, 3, 4, 5. And so the length of JK and the length of LM are both 5. So are these guys congruent? Yeah, they are. And so we can write segment JK is congruent to segment LM. Okay? So that's lengths of segments and congruence. Okay, and that gets us to our homework. Homework's out in Canvas. Make sure you get that done by next class, and we will see you then.